Alright, so in this video, we're going to go over these challenge problems from lessons 78 to 81, which you guys worked on this week. Again, make sure you watch this video, check over your answers, and feel free to use this to help you on your quiz on Quizizz. So, one of the lessons was regarding scale factors. How do we deal with things that are drawn like small or shrinked versions of actual things in real life, and so that's actually really common, especially when I look at blueprints for a job. So a scale drawing of a rectangular park had the scale that 1 centimeter is equal to 90 meters. So for every centimeter on this drawing, that equates to 90 meters. The question they're wanting us to ask or answer is, what's the actual perimeter of the park? So what I would recommend you do is to just draw a new picture, and then we're going to use the scale factor to draw what the labels actually are. So again, the idea here is that we can draw a small version of something that exists in real life with the correct proportions of the pieces from one side to another for the purpose of measurements and things like that. So what can we do to convert this? Well, it becomes a pretty simple conversion. We talked about in class. We're going to use a conversion factor. So 9.3 centimeters, we're going to multiply by something. We want the centimeters to cancel because we want to convert it to only meters now. So we're going to start with our drawing size, and then here they've given us a scale factor that for every 1 centimeter, that's 90 meters. And if you look, we're going to be multiplying here to cause what to happen. We're going to get the centimeters to cancel. So I'm going to go ahead and cancel that, and then all we've got to do is 9.3 times 90. We're going to get 837 meters. 837 meters. So that is this actual length. Alright, so continuing that same line of thought here, I'm just going to make sure I have my calculator handy. We're going to do the same thing for 8.2 centimeters to find the actual distance. So again, this is a scaled picture using this equivalency or this kind of conversion. Alright, so we're going to use the exact same thing here. We're going to do it for 8.2 centimeters times for every 1 centimeter, that's equivalent to 90 meters. So 8.2 times 90, and the cat's on the computer. Okay, sorry about that. So we get 738. So 738 meters. So at that point, we have our dimensions. Of course, since this is a rectangle, we can copy this one over to here. 738 here, and we're just going to add all these together to find our perimeter. So that would be what I draw my new picture here, but for the sake of time, plus 837 plus 837, we're going to get 3,150 meters. Again, that's what they wanted. They wanted the actual size of it based on a scale drawing. So again, scale factor. A lot of times you see it written like a 2 to 1, like that. But what that means again is one picture is exactly twice the size of the other. Well, this one's got different units, so that complicates things a little bit further. But again, you can kind of think of it the same way. 90 meters is 1 centimeter. You'll notice we see kind of like a little colon there. It equates to an equality sign. There's a lot of redundancy there in that statement. So 3,150. One of the other lessons we talked about unit conversions, standard, U.S. customary, and also metric. And so here we're kind of mixing the two together. You're welcome. So 2-liter bottles, sodas in 2 liters, whereas milk, half gallons or gallons. But if you take them and you compare them side by side, one of them, yeah, they have kind of a different shape for the 2-liter here, and then the half gallon's got more the square thing going on, and then like the handle hole. They're actually really close in size, like I said, or volume, or what we like to say, capacity in our book. So 2 liters is 53% of a gallon. That's really close to 50%, right? So use this statement to determine how many liters are in 1 gallon. So think about something. If we learned anything from the previous example or the ones in class, we want liters. We're starting with gallons, and we want liters. That's capitalized. Lights? No. Liters. So we're going to have to convert. We're going to have to multiply to convert. Again, a conversion factor, factor being a word that tells you to multiply. We're going to multiply our existing quantity, 1 gallon, times the conversion factor. So 53% of a gallon, we're going to convert that to 0.53 gallons. Why did I put it on the bottom? Because I want it to go away. I want liters in my answer. So notice I put liters on top, and I simply have the conversion factor numbers for my quantity comparison here. What I hope you'll see is that gallon is going to cancel, and I've got 1 times 2 divided by 0.53. So we will employ a calculator here for the sake of time. 2 divided by 0.53. We're going to get 3.77. And I rounded some. I stopped at 2 decimal places. So, don't look down, camera. Well, there it goes. So 3.77 liters. Again, if I could spell that. 3.77 liters. Now, I don't know about you. Your parents might remember, and they may still sell these. I don't think I see these much more but 3-liter sodas. Is anybody watching? Do you guys remember 3 liters? That was a lot. That was a big bottle of soda. All right. Nonetheless, conversion factors. Know them, use them. They're extremely helpful. Question 3, use what you know about the area of rectangles and triangles to find the area of the parallelogram below. Oh, no. Okay. Well, here's the thing. This has already got a major hint in this problem. You don't know what this side is. Some of you may have picked on it. It looks kind of like a rectangle that got like smushed over. When you're trying to build something and you don't have a triangular support, it kind of falls over. But what do we know about rectangles and triangles? Well, if I go ahead and draw this dotted line here, it means I've turned this into 2 triangles and a rectangle. Right. Here's the problem. This 15 measures this entire side. So we don't know what this dimension is. Yeah, it's less than 15. Looks like 9. You can't base it on how it looks. So the only thing we know so far is that the height is 8. And again, I'm gonna use base times height for my rectangle formula just for the sake of the words. I know sometimes we talk about width, but this is length and width. This is the same thing. Okay. Here's what I really, really want you to see, and I think it's super helpful to be able to think this way. So if I wanted to shift this triangle over, and remember, I can't find the area of this rectangle and then the area of these 2 triangles and add them up. That would be great, but I can't do it. What I'm going to have to do is actually imagine, and again, it's not pretend. I'm going to, hypothetically cut this triangle off and place it over here. Now, why does it match up so perfectly? It matches up so perfectly because it's a right angle, so it makes it a right triangle. Now, I know that's going to be there. It has to match up perfectly here because it's a parallelogram. And remember from our characteristics of parallelograms that our opposite angles are congruent. So this one and this one and those are all going to be the same. How nice is that? Contrast that with these obtuse angles here. Just a quick little review there. But all that to say this. What I've done is I've chopped off this triangle, tacked it on to the end of the parallelogram. Now what do you notice I have? I have a rectangle with the exact dimensions, 15 times 8. So my area of my parallelogram will actually be the base times the height. But make sure you see that the height is measured just like it would be in a triangle. It's an altitude. That means it's a right angle. So it would just be 15 times 8, or 120 square inches. Awesome. Let's keep going. Another scale problem. So Adrian is planning to drive from city X to city Y. The scale drawing shows the distance between the 2 cities with a scale of 1/4 inch is equal to 18 miles. So like I said, I use scales on blueprints all the time because you can't fit the actual size of the house on paper. that just wouldn't be practical. It'd be kind of weird. So we use that all the time, and a 1/4 inch is many times used for housing plans. Again, this is our conversion factor, so everywhere that we see a 1/4 inch, we're going to replace that with 18 miles. Well, there's two parts to this question. So the first thing I want to ask you is, how far is it from city X to city Y in actual distance or miles? So on the paper, this is 3.5 inches. So we've got to think, okay, 3.5. 1, 2, 3.5. So there's 1, 2, 3, and then I've got a half. Right? Okay, well that's 3.5 inches, but how does that help me with a 1/4 inch? Well, every 1/4 inch is 18 miles. We have to know how many 1/4 inches are in 3.5. Well, I can split each inch up into quarters. 4, 8, 12, 14. Well, the number line kind of is actually really helpful there. I have 14 1/4 inches. So this is 14 1/4 inch pieces times 18 miles each. Again, this is just a name, so don't use that number. 14 1/4 inch pieces and 18 miles each. That's 252 miles. So to do that another way, right, again, this used a picture. We would just say 3 1/2 divided by 1/4. How many times does a fourth fit into 3.5? And so hopefully you remember that we have to convert that to 7/2 when we multiply mixed numbers. We've got to convert it to an improper fraction. Then we're going to multiply, instead of divide fractions, we reciprocate or flip the second and change it to multiplication. So what do you do there? Well, you get 7 times 4, that's 28, divided by 2. Voila, hey, it's 14. 14 1/4 inches, and then 18 miles for each of those quarters. All right, so there's the equation basis for what my drawing is actually showing. Now, I haven't answered the question yet. We just figured out that it was 252 miles from X to Y. Okay, so we're going to say equals 252 miles. If he drives at an average speed of 30 miles per hour, how much time will it take to drive from city X to city Y? Oh, yikes. Okay, so 30 miles per hour. Look at what they're asking. How much time? Do you guys get a clue for how to do the problem from the question? Yes. How much time means I'm looking for time. What do I have? I know that I'm going to be doing 252 miles. How do I go from 30 miles per hour to a time limit? Well, let's just think about something. 30 miles per hour. So I'm gonna start out with 0 hours and 0 miles. I hadn't spent any time driving. I hadn't gone anywhere. After 1 hour, how far have I gone? Well, 30 miles per hour means 30 miles. Another hour, another 30 miles. Now notice I added 30. Another hour, another 30 miles. This is really slow. But stay with me. What am I doing here? I'm writing a table that illustrates the pattern here. What is going on? 210, I'm getting so close. So 8 would be 240. 9 would be 270. Oh wait, that's too much. I've gone too far. So 8 hours was 240 miles. What's the relationship here and here? Well, it must mean that the distance, which is 240, is equal to the time times the rate or speed. So check it out. I've got to go 252 miles. I know that I'm going to be going at 30 miles per hour. I don't know what the time is. So that's why the time is the variable. And so to make this really, really easy and a little crazy on my paper, I've got 252 miles equals 30 miles per hour times t for time. And hopefully you remember that with one step equation like this, I'm multiplying to my variable. I want to get rid of the multiplication. I'm going to do the opposite of multiplication. I'm going to divide by 30 miles per hour. Divide by 30 miles per hour. So here's what I got. I'm running out of paper here. 252 miles times, remember we're going to change division here, times 1 hour over 30 miles. Now what just happened there? I was dividing by a fraction, 30 miles over 1 hour, right? You did see that as a fraction. And I changed the sign and I flipped the fraction. Yippee. What happens? What's the importance? The miles are going to cancel and I'm left with hours. Is that what's right? Well, go back to what I said earlier. The question is how much time. So I want hours. That's what we're supposed to do. Last step is to go ahead and type that in. 252 divided by 30. We're going to get 8.4 hours. Now, does that match up with my table? I hope the table made a lot of sense to everybody. Remember in my table we said at 8 hours, 240 miles. At 9 hours, 270. I passed 252. So my answer of 8.4 makes perfect sense. All right, let's make it a little simpler. Cora was 4 feet tall at the beginning of 4th grade. Coincidence, I think. If she grows 3 inches per year at the beginning until the beginning of 9th grade, how tall will she be at that time? So let's first understand t must equal 5 years. 5 years are going to pass. We've got a rate here. Again, how do you identify a rate? Look at the units. 3 inches per year. Inches per year. It's a ratio. It's a rate. Those are the same thing. So I've got 3 inches per 1 year. How tall will she be at that time? So give your answer in feet-inches. Here's what we got to do. 3 inches per year until the 9th grade. What do I do? Shall we make a table? We're going to do time and height. Now, why did I choose these? Because a rate is the number that you're going to use to make your table. It's going to be the pattern-based number. So after 0 years, we haven't grown any. After 1 year, 3 inches per year, I will have grown 3 inches. Maybe I should do it this way. Maybe we should say 4 foot 0. 4 foot 3, and that would be at the end of 5th or the beginning of 5th grade. 6th grade, 4 foot 6. 7th grade, 4 foot 9. I don't know if she's 4 foot 9 yet. Well, that makes sense. 7th grade, we're close, right? 4th year, we'd be at 4 foot 12. No, we don't say that. That's 5 feet even. In the 5th year, because we said, hey, it's going to take 5 years, 5 foot 3. You think Cora's going to make it at 5 foot 3? I guess we'll see. Determine the growth rate of a tree which has been measuring 4 inches of growth every 5 months. Now, this one's related to the problem previously, but they want it in feet per year. So 4 inches every 5 months. We're going to use this rate. That's what it is. It's a rate. Again, we identify it the same way as the last one. It's inches per month. We're going to say, okay, well, that equals how many feet, in 1 year. Again, they want it in feet per year. They tell us that. So what we've got to do is think, well, yikes. We can convert these. 4 inches is what fraction of a foot? Well, 4 out of 12, that's 1/3. So we can change 4 inches pretty easily to 1/3 of a foot per 5 months. Equals 1/3. I'm sorry, it doesn't. We don't know how many feet that is. Some number of feet per year. Oh, yeah. All right, so how do we finish this? How do we finish this? Move that back just enough. We've got to convert 1/3 of a foot. No, we don't. Maybe we do. I don't know. 5 months. So here's the thing. I want to take 1/3 feet per 5 months. I'm going to do this twice, okay? See if I have enough room. 2 conversions. Or maybe I've already done it. I don't know. Let me do that. Let me do it this way from the beginning. That would probably be better. I know you probably understand the 1/3 foot thing, but let's try it this way. We'll try to simplify this process. 4 inches every 5 months. We're going to use these conversion factors just like the first few problems. I want inches to go away, so I'm going to do inches here, and I want feet to show up. What's the conversion there? 1 foot, 12 inches. Okay, great. What about months and years? Well, I want years in my I want years in the answer, and you can kind of see that months is on the bottom. So if I want months to cancel, I'm going to put it up here. So months and years here. Let's make sure of something. Are the units going to cancel so that I end up with feet per year? Well, the inches are going to go away. The months are going to go away. I just have to know how many months are in a year. 12. 12 months per year. Now, follow this. Go back through that really quickly. Feet per year, the only units that are left. So here's what I'm going to get here. 4 times 12, that's 48, over 5 times 12, that's 60. We're going to reduce that to 4/5, and then we're going to get feet per year. 4/5 of a foot per year.